Hello, my name is Igor, and in this video I am testing Polymaker's PolyMax line, PLA, PETG and PolyCarbonate. A few weeks ago I did similar video where I was testing a PolyLite line, 5 different types of the filaments. And I will repeat those now, my standard experiments, so the results will be comparable with each other. On the page you can download the Excel files so they are comparable. And as you can see, these are new boxes, they are sent to me by Polymakers, and I will use them exactly after opening out of the box. So I will not dry them because I think PETG is a little bit sensitive to moisture, but I will not dry it, I will just open it exactly before I will start with the printing. And from these three, polycarbonate requires a little bit higher temperature, and also it will be printed inside the enclosure. Just quickly a few words about these materials. PolyMax PLA. Well, for PLA we know that it is easiest for printing, and this version PolyMax is better on impact strength compared to the regular PLA, but I think it sacrificed some tensile strength of it, but we will see this in the mechanical testing. About PETG, we know that PETG must be dry, but I will not dry it, I will use it out of the box. And that's what you should do. Print it, and immediately after printing, put it back in some resealable bag and put some silica gel inside. From this graph I can see it is good all around filament, and it is better on impact strength compared to the regular PETG. And about the PolyMax polycarbonate, it can withstand a load up to 113 degrees Celsius. And from this graph I can see that it is better on tensile strength, bending strength and in impact strength compared to the regular ABS or regular PLA. But also it is important to know that polycarbonate requires higher printing temperatures, and also it has to be printed inside the enclosure to prevent some warping or cracking of the object. And all test specimens will be printed on my Industry V2, where I have the microsys all-metal hot end and the direct drive extruder. And now let's see this PLA filament. In a box we have a sticker and some instructions. And pay attention that this is resealable bags. It has don't open from this side, but from this side, and open it with the scissors, and then in that case you can place it back and close it after the printing. Very nice transparent spool. Let's see what info we have on it. Two scales. On this side we have it in meters and this one is in grams. And since the printing temperature is between 190 and 230 degrees Celsius, this temperature tower will have 5 elements, but starting from 230 degrees. It just started the third element, and interesting, I can see here some curling up, so it has some problems on 60 degrees overhang on highest temperatures. Printing is finished. Let's check the bed adhesion. Okay. Actually not bad temperature tower. The bridging came out perfectly, no stringing on any temperature. Only problem I can see is on the overhang on these two highest temperatures, but these three are quite acceptable, but everything I will print on 210 degrees Celsius. The bed surface already cooled down, so it's very easy to remove them. The next material is PolyMax PETG. Sticker and instructions. And don't forget every bag is resealable, so cut it on proper side. And again, nice transparent spool. Information on the sticker, the printing temperature between 230 and 240 degrees Celsius. So this temperature tower we have only 2 elements. And again, here we have here the scale to see how much filament we have on the spool. Don't forget, some cheaper PI sheets may stick too good to the PETG, and when you remove the objects you may break down the PI part. This is PEX from the Van Bam. But if you have some cheap PEI, in that case maybe you would like to use glue stick or something like that as a separation agent. Now sometimes the PETG may absorb moisture from the air, and in that case you will have more stringing during the printing, but I will use it as it is now out of the box, and I will see if there is need some drying. And immediately after the printing I will place it back to this receivable box and place some silica gel inside. In case you have some very old PETG and you have a lot of stringing, in that case you can still save it by drying in some filament dryer. It's printing the second, which is also the last element. The part cooling fan is on 15%. Printing is finished, and before it cools down, immediately I always want to check the bed adhesion, which looks like great. Quite decent temperature tower. The bridging came out great, very minimal stringing I can see. This means the filament is dry. Only problem I can see that it has some problems on the 60-degree overhang, and the reason for this is the weaker part cooling. I left it to 15%, but it was more than recommended, which is to completely disable the fan. Anyway, I print all test specimens on 235 degrees Celsius. It's already cooled down. And as soon as possible it goes back to the resealable bag with some silica gel inside. Polycarbonate. Sticker and instructions. And resealable bag. Printing temperature between 250 and 270 degrees Celsius, so this temperature tower will have 3 elements. It's still printing the first element at 270 degrees Celsius, and there is no sign of the warping, so the first layer sticks good to the bed surface. Well, it's almost finished. This is the last element on 250 degrees Celsius, and then I will wait until the bed surface cools down, and I will then remove the temperature tower. And the temperature inside the enclosure was approximately 46 degrees Celsius. The bed already cooled down. This temperature tower looks great. Maybe the bridging is not so perfect, but there is no stringing, and look at this almost perfect overhang. And now I print the test specimens on 260 degrees Celsius. So far so good. That's the perfect first layer, and I'm printing everything on 250 degrees Celsius, and I'm using only 12% cooling. Officially it's not recommended to use any cooling, but 12% it's not much, but I have to use because of those big overhangs on those vertical test specimens. Looks okay so far. I cannot see any signs of the warping, and the temperature inside the enclosure is 45 degrees Celsius. Well, actually now I can see some warping on the two objects. Maybe I should use the brim, but I forget to enable it on this printing. PLA, PETG, polycarbonate. Far the best is the polycarbonate. Tensile test. These objects are printed in horizontal position and the smallest cross-section area is 4 by 4 millimeters. And I want to record the breaking load in kilograms. They all broke properly on the smallest cross-section area. For the filling, the polycarbonate was the strongest, but I will analyze the results later in this video. And now let's check the layer adhesion. These test objects are printed in vertical position and the smallest cross-section area is 4 by 4 millimeters. And I want to record the breaking load. Well, I hope the load will not be too big because I will use my own weight for the breaking. But you don't want to see it. Well, for the filling everything is okay with the layer adhesion. Maybe the weakest was the PETG, but the polycarbonate was the strongest. And only this one test specimen didn't broke properly on that smallest cross-section area, but it was very strong. And now the shear stress. The diameter of this test specimen is 5 millimeters, but the area is doubled. One part from PETG is missing, but they was shared properly on those two cross-section areas. This means in 3 pieces. This is 3-point bending test based on ISO 179. The distance between supports is 50 millimeters, and I want to record the load at 2 millimeter deformation and the maximum load. PolyMax test objects after this bending test, and look at this PLA, PETG and polycarbonate. They just deform and they didn't broke, and the formation is quite equal. In this torque or twist test, this test object has the diameter of 6 millimeters, and this side goes into the vise and the other side goes into the torque meter, and it can record the peak of one movement. And I want to record the torque at 90-degree rotation and the braking torque. 1.3 and 1.4 was the peak. 1.1, 1.3, 1.4, 1.7, 2.3 was the peak. And this is how they broke or deform, and I could feel that I could do at least 1 or 1.5 rotation before the load or the torque starts with reducing. With the size of the impact test, I want to see how brittle or how tough is this material. I have here these notch test specimens, and this is half kilogram hammer, and it will swing to the other side. This is the 0 position. But then I will place here the test specimens, it will break in and swing to the lower position, and from difference in height I can calculate the potential energy used to break this test specimen. Zero position, PolyMax PLA, PolyMax PETG, PolyMax PC. And interesting, after the test only the PETG broke completely, PLA not, but this was very tough, the polycarbonate. And now let's analyze the footage. So this is the scale, and this is the zero position of the hammer, and this is after breaking the PLA, PETG, and the strongest polycarbonate. And if I left only these lines and calculate the distances from the zero position, I can calculate the energy used for breaking the test specimen in joules or in kilojoules per square meters. And it's time for the temperature test. This is the sensor for the thermometer. I want to record the temperature when they start with the deformation. And I already know the order, so probably it will be PLA, PETG, polycarbonate. Only I'm curious on what temperature. This is a time lapse of approximately 4 minutes, and I try to catch the temperature the moment when they exceed approximately 0.4 mm deformation. And I can stop the experiment here. So no big surprises, only you have to check the footage to see at what temperature they started with deformation. And I want to measure the hardness with this short D durometer, and I still didn't got any help in the comments, but I asked for it. So is this important for you? I mean, what kind of application requires harder material? I mean, I know with the metal that harder material is more wear resistant, but I'm not sure what is the case about the plastic. But anyway, I will measure it, so we will see in the future is that useful or not. PLA 7.5, 70.5. 69.5. PETG 69.5. Polycarbonate 74, 73, 73. So polycarbonate was the hardest, and everything was measured perpendicular to the layer direction. Let's prepare the bending grip test. I have these C test specimens, and distance between these two surfaces is 12 mm. And the gripping is the deformation of the material during the constant load. PLA PETG polycarbonate, and I will place this 1.25 kg load, and I will follow the deformation. And for more accurate measuring, I am locking the position with this 3D printed part. PLA 15.93, PETG 16.31, polycarbonate 14.72. Day 0, Day 1, Day 2, Day 3, Day 4, Day 5. The oven was preheated. And this is the sensor for the thermistor. The temperature of the oven is not too accurate at the beginning, but when it's stabilized, it is very constant. But just in case, I'm supervising it with this thermometer. This is the current temperature, 47 degrees Celsius, and this is the alarm temperature, just in case. And now, after 1 hour, I have to take them out and analyze the pieces. So this was day 5 before the heating. And this is still day 5 after 1 hour of heating on 47 degrees Celsius. And at the end, I always like to record the removing of the load. And this is how they look like after 10 minutes. And all the data I will process with Excel. And now I am preparing the second type of the grip test, which is that screw test. And now in a vise I will hold only these nuts. All bolts are tight, and tomorrow I will see if I can move them even more using the same torque. And let's see what is the situation after 24 hours. Day 1. Day 2. Day 3. Day 4. Day 5. And now let's see the deformation after the heating. And all data will be processed into Excel table. And now let's analyze all the results. I will start with the creep test, and this is the raw data from my bending creep test. This distance between these two surfaces which I measured. But this is not what we need. We need actually the creeping, the deformation between these two days. So that's why I prepared this table. And actually the 0 means 0 creeping, that's the best. There are some negative values, but that may be some inaccuracy in measuring. And this is after the heating. The screw creep test is already in the differences. So here the 0 means no creeping. And here we can see some additional informations. These are in megapascals because I prefer this kind of values because it's easier for understanding for non-mechanical engineers. That if I tell you that 4x4 millimeters broke on, I don't know, 100 kilograms, it's easier to imagine the load compared to these megapascals. But anyway, I left here these data because these are given in specification tables. Here we have this same with the IZOD impact test. But let's analyze this on graphs. So this is the creeping, this is the bending test, and this is that screw test. And as we can see that it starts with the creep after maybe third day, the creeping stopped, and after the enclosure, well, actually we can see that the PLA deformed a lot. And very similar results we have that on that screw test, creeping. Tensile test, layer adhesion test, and shear test. The load is 200 kilograms here, so they are comparable even with each other. And we can see that the polycarbonate was the strongest on tensile test. On layer adhesion test, they are quite equal. Maybe the PETG was a little bit weaker. And on the shear stress, again, the polycarbonate was the strongest. The bending and torque test, and usually I notice that they are quite similar, so we can see again that polycarbonate was the strongest, especially on the maximum torque. And now this is very important for these PolyMax materials. And look at this, so polycarbonate was far the strongest on that IZOD impact test, and the weakest was the PETG. And this is the temperature test, and again the polycarbonate was the best here in this case, and the PLA, well, as every other PLA, a little bit of 50 degrees Celsius, it starts with the deformation. I was expecting a little bit higher temperatures here with PETG, but that's close. And the hardness, and as I mentioned, the hardest was the polycarbonate, but I'm still not sure if we need these informations in different applications. So let's talk about the PolyLite versus PolyMax filaments, because I was curious, and actually everything is given in these Excel tables and you can process the data yourself, and I wanted to prepare this comparison for my Patreon supporters, but I decided to present it here in this video. I will find out some other gift from my Patreon and Buy Me a Coffee supporters. Maybe I will collect all the data from all my material tests in one table, and that will be my gift maybe at the end of this year. Okay, back to this PolyMax versus PolyLite comparison. So this is only the mechanical test comparison between PolyLite and PolyMax filaments, and I copy here the data from previous Excel tables. So here we have the PolyLite PLA and the PolyMax PLA data. In this part we have the PETG, and this is information for the polycarbonate. And here we can see the type of the mechanical test. Now this is the comparison table, so I took the bigger value as 100% and I calculated the smaller value in percentage. That's how I got this table, and this I want to analyze on graph. This is the PolyLite PLA versus PolyMax PLA in percentage, the comparison, and we can see that the PolyLite PLA was stronger in mechanical tests compared to the PolyMax PLA. Well, the difference you can see here in the graph, but on IZOD impact test, the PolyMax PLA was, I know, 3 times stronger compared to the PolyLite PLA. So that's why it is important to understand this, and so you can choose the correct material for your application. Because if you are expecting some dynamic load impacts, in that case the PolyMax PLA is better for that. But if you don't expect these dynamic loads, in that case basically for all other specifications the PolyLite PLA is better. Now let's see the PETG. Again, it was better in all mechanical tests, the PolyLite, but the PolyMax was better on IZOD impact tests, but the difference is not so big. So here actually I would perform the PolyLite PETG because it has better mechanical specifications. Now the polycarbonate, here we have a little bit different story. Again, yes, the PolyLite was better compared to the PolyMax on all mechanical tests, well, except here on maximal torque, but the difference is not so big. But look at this impact test. So here we have huge differences. So the PolyLite PC is extremely brittle, but the PolyMax PC is very tough material. So definitely, basically, in this case, I would always choose the PolyMax PC because of these specifications. So this is the end of the Polymaker's PolyMax filament testing. And I know it is a very long video, but I cannot make it shorter. Sometimes I need these footages for myself too later. But don't forget, you can always contents down in the description so you can jump to any part of the video you would like to see. And maybe you didn't even notice, I have to mention again, but there are no ads during the video. About these same materials, yes, the PolyMax PolyCarbonate was the strongest, but it is hardest for printing, so it requires higher temperatures, and it's better to print inside the enclosure. And don't forget to use the brim. I didn't use it, so I got warping on 2 elements. Of course, the easiest for printing is the PLA. And but don't forget, the PLA, unfortunately, it will deform a little bit above 50 degrees Celsius. So if you forget your part inside the car, on hot summer day it will deform. So the PETG is a little bit better solution if you need a little bit higher temperature resistance. I hope I could help you a little bit so you can see that first you have to understand your applications and what requirements you have, and then I hope this video will help you to choose the correct filament and material for you. Okay, thank you for watching and happy printing!